Hello and welcome back to the CPU design example. You recall what we've done so far is design the data path by first of all breaking down the instructions into required sequences of microoperations and then reworking those sequences of microoperations to try to produce the most performance efficient design. And this is that design. What also is shown here is the interface to the controller. All the control aspects are in color. Again, looking at the data path, you see the ALU, the A and B registers, ALU out, the register file, the instruction register, the memory data register, the program counter, and the memory. And you notice all these muxes here, which are because there's micro operations that use resources in different ways. So for example, the address to the memory either comes from the PC for instructions or it comes from ALU out for store word. And there's many muxes in this design. Now you'll notice that a lot of the control lines are basically the select lines to these muxes. And in fact, all the muxes in the data path are the select lines, are control lines coming from the finite state machine controller. There's also control lines that are write enables for registers. For example, this line is a write enable for the program counter. If that depends on these two control lines and the zero flag coming from the ALU. You'll also notice that there's lines going from the data path to the controller. In particular, the top 5 bits of the instruction register, which contain the opcode which specifies the type of instruction, e.g. ALU or load word or so on. You'll also notice that part of the controller is this combinational logic block ALU control. The ALU does a number of things beside ALU operations. It also does the PC add, it calculates addresses for branches and jumps, or not for jumps, it calculates addresses for branches and calculates addresses for load word and store word. Thus, we need a controller from the ALU, and the two inputs you notice for that are part of the instruction register. This is actually the function field for the instruction register, which is used if it's an actual ALU instruction, and ALU op from the finite state machine, which specifies whether it's an ALU instruction or whether we have to do an add for an address calculation. So that completes an overview of this design. Feel free to pause and look at it in more detail. The next step is to work out the design of the controller. And this is relatively straightforward. The first step in doing that is to identify all the control lines. Most of them are either enables to the memories or registers, or mux select lines. In addition, we have the ALU control lines. We have two status lines coming from the data path, the zero flag from the ALU, and of course the opcode from the instruction register, which tells us what type of instruction this is. The easiest way to approach the controller, in this case has to be a finite state machine because there's branches within the state sequence, is to first of all sketch out the micro operation sequence in a finite state diagram format. So that is what I've done here. In the first cycle of every execution of every instruction, we fetch the instruction increment the program counter. In the second cycle, we calculate the possible branch address, and we don't know whether it's a branch or not at this stage. In this cycle, we know what type of instruction it is because now the opcode has been presented during this cycle to the finite state machine. Based on that opcode, we then execute the series of operations required to execute that instruction. Load word and store word, calculate the address, read or write the data. ALU operations, do the ALU operation, write it back to the register file. Branch, work out if we're going to take the branch or not, modify the PC if we are, jump, modify the PC. You might have noticed that A and B being written to has disappeared from this. And the reason for that is it's not controlled by the controller. We'll end up doing it implicitly in the data path. That is, whenever the addresses on these two read ports change, which happens whenever the instruction register changes, the instruction register will do a read automatically, and in the next clock cycle, the results will appear at A and B. Thus, in this cycle here, A and B are modified without the need for any commands from the controller. Thus, we don't put that microoperation into the controller microoperation sequence. It's not being affected by the controller. This then translates into specific settings of all the control lines going from the controller to the data path. These are the settings on the control lines that allow those micro operations to happen. Many of these are mux settings. Some of these are settings of ALU op, telling it 00 means do an add, and so on. I'm not going to go through all of these. I'm going to leave that as an exercise for yourself if you so choose to. It largely corresponds to things we want to do in this micro operation sequence. But I will illustrate some of these in the next few slides. So again, we've actually now completed the design. We haven't done the Verilog. I'll come to that in a little while. But I just want to summarize again the key points we've done to achieve this point. We determine the algorithmic intent, the design specifications and objectives. We determine the micro operation sequence. Both the micro operations are required and their optimal sequence. Notice we design the data path first. We then identify the status lines and control lines that are needed. We design the controller second. Because this controller has a complex control sequence that depends on information from the data path, it is a finite state machine. Just going to illustrate some of these states. This is state 0. In state 0, we fetch the instruction register. We do that by setting the control line to this mux to 0. That's the ILD, so ILD equals 0. And we set memread. We have a memread enable in this particular example. We set memread to 1 to tell the memory to actually do a read. We set IR write to 1. That is the write enable for the instruction register. So what happens in essence, program counter goes to the address port of the memory. Instruction comes out of the data port, and because of this write enable is written to the instruction register. The other micro operation that's being performed here is adding 4 to the PC. This top mux here is set to 0. This is ALU source A. That comes from the PC. So it's connecting the PC to the ALU. This bottom mux, ALU source B, is assigned to 1. That means 4 is selected as the input to that mux. ALU op is equal to 0. That says add. So we're adding the PC to 4. So PC plus 4 appears here. We set this mux, PC source, to 0 to select the output of the ALU. We set PC write to 1, goes through this OR gate, does a write enable to the PC, so the PC is actually written to. This is an example of how individual control lines are set in order to enable the specific micro operations that have to be performed in this clock cycle. I then go on, and I'm not going to go through the details, showing this for the additional states in this finite state machine. In this state, we still don't know what the instruction is until during the state. It is calculating the branch target address. and writing to A and B automatically because the instruction register changes. This state is the execution state for the ALU, doing the ALU operation. Set these muxes appropriately, writes to ALU out. This state is doing write back to the register file from ALU out through this write data port here. The address for that is selected from the instruction register. This completes the branch equals. PC is overwritten if the 0 flag is high, based on A minus B. This completes the store word. This calculates the address for a store word. This completes the store word. That is ALU out goes to the address of the memory. B goes to the right port, the right data port for the memory. This processor also handles exceptions and interrupts. I'm not going to go through this in a lot of detail. I remind you, an exception is an internal reason to interrupt program flow. In this particular case, we want to detect overflow. An interrupt is an external reason, such as an I/O device request. What we're going to do in this processor is have a cause register that we write to, have an exception program counter, which is the return address, and then set the PC to this address to start, at which point the exception handler takes over. We're going to only handle two exceptions: overflow and illegal instruction. To do that, we're going to add these two registers that we need: the exception program counter, which is the return address, and the cause register, indicating whether it's an overflow or illegal instruction. We also have to modify the finite state machine. These are the modifications for the finite state machine. Overflow only happens on an ALU operation. So if overflow goes to 1, because we added an overflow flag coming from the ALU. Correction, no, because the cause register is telling us that. If overflow is equal to 1, we jump to this state, which basically jumps to the exception handler. We detect a legal operation in this state. If that occurs, again, we execute this state, which jumps to the exception handler. Now let's look at the Verilog implementation for this design. I'm going to start off with the data path. And we're not going to go through the whole thing in detail, but you can see here the ports to the data path and the port declarations, and the local variable has actually been defined through the data path. I'm going to put that aside for a moment, but we'll talk about some of the details selectively within this. Here's a detailed example of part of the Verilog mapping onto the data path. Here's the PC. If reset is low, and I haven't explicitly shown reset in this data path, but it is needed and must go to the PC, as well as to the state machine. If PC is low, then we set the program counter to 0. That's presumed to be the start address upon reset. Else, if PC enable is high, which is this line here, PC equals next PC is the name of the signal here. Here we have the mux for next PC written out as a case statement. So it's writing to next PC from ALU out, from the out, which is either the output here or the output from the register, from a jump address calculation, or in the case of an exception, from C0000000. So this shows piecemeal logic for the PC and the mux for the PC. You notice I've just broken these out as procedural blocks. It is using the same coding styles that we've been going through so far. I want to detect overflow for the overflow exception. Here we have signed arithmetic. It's not unsigned arithmetic. And to date, I've never actually gone through how to detect overflow in signed arithmetic. Here's some simple examples. If we add -7 to -7, you'd expect that to overflow, right? This new word, remember the top one here is the carry out, is not -14. In fact, it's a positive number. Let's show that it overflows. If you look at this carry out XORed with the carry out from the 3rd bit to the 4th bit, you notice in this example that that is 1. And that is actually in general how you detect an overflow. Here's the opposite example, -7 plus 7. Here's the carry bits. We get 0, the expected answer. We don't expect an overflow. And in fact, if you look at carry 4 XORed with carry 3, it's 0. Here's 7 plus 7. We'd expect this to overflow. Here are the carry bits. Here is the sum. It says -2, which is not what you expect. You expect 14. Again, if you look, carry 4 XOR with carry 3, that is equal to 1. All I'm illustrating here, I'm not proving it, I must admit, but I'm illustrating that you can detect a signed overflow by XORing the carry out, which you might recall is how we detect an unsigned overflow, XORing that with a carry in into the most significant bit, carry 3 in this particular 4-bit example. Here's a piece of code that actually does that. What I've done is done an add on the bottom 31 bits, explicitly naming the carry out from the most significant bit -1. Here I've done the last stage of the sum, just for the 31st bit. This gives us the carry out of the total adder. I XOR those two together to set the overflow flag. So again, this is the final design that matches onto the Verilog that you see here. I'm not going to go through this in a lot of detail. Again, you see the program counter, the instruction register, EPC register, the memory data register, and the A and B registers and the ALU out register. Here is the register file. I gave an example of this earlier in the Verilog 2 notes. This is slightly different coding, but it's much the same. Here I've declared the register file. Here I'm setting the muxes on the inputs to the register file. Here I'm writing to the register file. Up here I'm reading from the register file. There's 2 read ports on this register file. Again, I've used a simpler coding technique than what I illustrated in the Verilog 2 notes. I will admit this simplified coding technique here will lead to a slightly bigger, slower design. I mainly used it here for compactness. If you want a more efficient design, I suggest using a technique such as I described in the Verilog 2 notes. Here's the ALU control logic. I've lumped that into the data path here for simplicity. It's taking the func field for the instruction register or ALU op from the controller and working out what operation the ALU has to actually perform. Usually it's an add. Here I have details of the ALU. Here I have the 0 flag. Here's the actual adder and the overflow flag. I give overflow a different name. I really only care about the overflow if I'm doing an ALU operation, and that is what this line is doing here. Some other a collection of muxes, more muxes, cause register, sign extension, done using much the same techniques we've shown before, just concatenation and replication. A fixed left shift for address calculation, and the jump address calculation. That's the ALU. Next, turn to the finite state machine. Here, this pretty much follows the template I gave in the finite state machine notes. Call it controller, declare the input and output lines. We parameterize the state machine encoding. I've also parameterized the op field encoding. R-type means an ALU operation. Load word, stored word, branch equals, and jumps. This makes it more readable. That's all that it's doing. We then have our combinational logic, which I lumped together. I actually did 2 case statements here just to make it easier to read. It possibly more efficient to have more efficient logic to have 1 case statement at the expense of readability. The first case statement here just works out the next state. So here we are in state 1. Depending on the opcode, if it's a load word, we go to state 2. If it's a store word, we go to state 2. If it's an ALU instruction, we go to state 6, and so on. So this is just to specify the state sequence. In the same always at positive, always at clock, blah blah blah. In the same always at block, I've also done the output logic. Remember, the output logic shares some logic with the next state logic, so we want it in the same procedural block. Here, what I'm doing is I initialize all the control lines to 0. Makes it much easier to write the actual case statement and prevents unintentional latches. Here are the case statement, selectively setting control lines to 1 based on what the actual state is. This is a Moore machine. And this toggles the actual control lines depending on the state. I then have the state register. Again, reset is applied to the state register. The reset state is state 0, else current state equals next state. So that completes the Verilog of the design. I've now one thing I want to at least present to you in a summary form, and that is how to pipeline the design. So when I've said pipelining so far, what I've really meant is breaking up a critical path into a series of smaller stages. Here we're actually pipelining the design. That is, we're going to let instructions overlap. We're going to allow up to 5 instructions to be executing at the same time at different stages within this one piece of hardware. What this example allows me to do is actually allow me largely how to illustrates how to design a pipeline controller. So what I'm going to do is I'm going to break each instruction execution into 5 stages. Instruction fetch, where we fetch it and modify the program counter. Instruction decode, when we write the A and B registers. Execute stage, where we do the actual calculations. Memory stage, where we read or write to memory. I'm only showing read here. And the write back stage, when we write back to the register file. By breaking it up like this, I've got one major piece of hardware that is only being used in one pipeline stage. I'm breaking the memory into 2, an instruction memory and a data memory. In the instruction fetch stage, we're only using the data memory, and we're going to add an ALU specifically for this stage. Instruction decode stage, we don't know what the instruction is until the end of this stage. In the instruction decode stage, we're prefetching A and B. In the instruction execution stage, we're only using the ALU, though here I'm using 2 ALUs, so I have to add a 3rd ALU as well as the PC increment ALU. Because remember, these can all be going, this and these operations, micro operations, can be going on in parallel. In the memory stage, this is the only stage in which I use the data memory. In the write back stage, this is the only stage in which I'm using the write ports on the register file. Up here, I was using the read ports. This is the integrated data path and controller for this. You can see we've broken it into stages. In between these stages, there is information we have to pipeline to pass on to the next stage in the pipeline. Again, this first stage fetches the instruction, stores it in the instruction register. In addition, we calculate PC equals PC plus 4, which is likely to be fed back to the PC. Actually, would be fed back to the PC. In this next stage, we're reading from the registers. Those reads, A and B, go into here. We're actually going to use the sign extension part of the instruction for address calculations later, so we have to put that into a pipeline register to preserve it for the next stage. The opcode goes from the instruction register to a piece of combination logic controller. There's no quote-unquote state in the state machine. The equivalent states are actually in these registers out here. We're essentially pipelining the state. Though we're not actually pipelining the state, we're actually going to pipeline the control bits. So this works out the actual control bit settings for the next 3 stages for this instruction. It works out what has to be done in the next clock cycle when the instruction reaches here on the next stage, and stores that in this execute register. This memory register stores the control bit settings for 2 stages later for this particular instruction. The write back stage stores the control settings for 3 cycles later for this particular instruction. So we're not going to pipeline the state, we actually pipeline the control outputs determined by this controller here. Remember, the idea is here that we can have different instructions in each of these 5 stages of the instruction register. So we have to keep the data associated with the instruction coherent with the control associated with the instruction. And that is what we're doing by adding these registers as shown. The execute stage, there's an address calculation and an ALU calculation. So we need 2 ALUs for that. Well, more specifically an ALU and an adder. And this execute controls what's happening in those. In the memory stage, we're reading or writing from the instruction memory based on what's in this memory control register that is still now coherent with the data because ALU out is basically here. In the write back stage, we now only need the write back control lines. That determines what is written back to the register file. And though this is drawn in this stage here, writes to the register file happen as the last stage of instruction execution as controlled from here. So this illustrates, I must admit fairly quickly and a fairly high level, how pipelining is done, very explicitly how the finite state machine changes. The input for the finite state machine is the opcode. Instead of a finite state machine, this control logic basically determines all the possible control settings required for this instruction in the rest of the pipeline. And it stores those control settings in registers which are themselves pipelined so those control settings stay coherent with the execution of that instruction as it passes through the multiple stages. If you want more details on this, I suggest going to this reference here where I've taken this figure from. So that completes this particular example. Again, major things I'm emphasizing: work out what micro-operations are required to execute your algorithmic intent, in this case the instructions. Work out how to sequence those micro-operations. Manipulate your design and that sequence and the actual micro-operations to try to work out a reasonably efficient design. Once you've done that for the data path, identify your control lines, identify your controller. If you're choosing to do a pipeline design, then your controller changes because all the control output is worked out in the first stage of the pipeline, and you essentially pipeline those control bit settings through the multiple later stages to keep them coherent to the data and instruction that's going through. And by the way, down here you'll notice that parts of the instruction itself are also pipelined. For example, this is the write register address part of the pipeline. So I hope this example was useful to you. It's a fairly large and complex example, but I really wanted you to see a much more complex example in terms of the richness of the micro-operations than the motion estimator that we went through. I hope this was useful to you. Thank you very much for your attention.